Morning. Let's start our morning session. So the first speaker is Peter Koroteev from BIMSA, and he will talk about Q-difference connection and p-Curvature. Please welcome.
Thank you very much. Good morning, everyone, and Happy New Year. Right. So I apologize for my voice. Well, this is not how I normally sound like, right? So I hope I can still be audible and yeah, like yes. So this is the project I've been doing with my very good friend Andrei Smirnov. He's now a faculty at North Carolina, and well, it's an attempt by ex-physicists / algebraic geometers to learn some number theory. Well, so I don't know pretty much about anything about number theory, but I'm going to talk about it anyway. So, so I'm going to stack it here. So so I'm going to explain what p-Curvature means and how to think about it. And I'm hoping that you guys who are experts in the field can give us some suggestions and comments. So well, you're very welcome. Okay, so now the key object of study is enumerative geometry of Nakajuma quiver varieties. Right. So by now there's a well-established study of those. People understand them very well. So if you want to have a kind of review paper, so there's a lecture notes by Andrei Okounkov around 2015. So if you put Okounkov, you put K-theory, and then the lectures will pop up. So now I'm not going to be able to explain all the nitty-gritty, all the details of the construction, but I'm going to in part rely on your intuition and kind of understanding of the thing. So in a nutshell, this enumerative geometry is governed by Q-difference equation. As you know, there's always should be some kind of master equation, and here in this story there are several. So the one which is relevant to us looks like this. So I'm going to write it down, and then I'm going to explain. Maybe I should write bigger. So I'm going to explain notation. So well, psi is the unknown function, or rather the vector function here. So m, so you see it's a certain Q monodromy equation, right? So here Q is the curve counting parameter. Z is a tuple of all Kähler parameters. It's like the Kähler torus. So let's say it's Nakajuma quiver variety X, right? And then so this is the Kähler torus of X. A is the equivariant torus of X. Okay, and then L here is a line bundle from a Picard group of X. Right, so Picard group is just a free abelian group, right? Which is the so it's essentially what is like it's space of Holmes from if V is the set of all vertices of a quiver, and then it just as a vector space is just well, it's z to the number of nodes in a quiver diagram. Okay, so and then m is some operator which we're going to discuss here. So the sort of the rough picture of what's going on is the following. So we have CP1 Riemann sphere as a source curve of the quasimaps, and then you have, if f is a quasimap, you map it into X, right? And then here the so there's a moduli space of such maps, right? So the or quasimaps rather into X. So you're studying all. So f is some kind of polynomial function of the parameter. So no, it depends on point on the base curve, right? And then it depends on the data of the quiver variety here, right? So the yes. Now it's the it's the group. It's like the so if well, if say your quiver is like this, then it's what SL4, right? It's the root system which is given by the diagram. Yeah. Okay, and then so on the moduli space you have action of the equivariant torus here. So this is T well A. That's the equivariant torus. So this variety X has quiver, has scalar parameters, and then there's also action of the C star Q on the base curve. It has two fixed points, 0 and infinity, right? So we're kind of working equivariantly with respect to this to this action. And then what else? Yeah, right. So the and then quiver variety locally looks like a cotangent bundle of some symplectic space. So additionally, there is another C star action here, which we call C star H bar, which dilates the cotangent fiber. So it takes all the coordinates in the cotangent direction and multiplies them by this non-zero number H bar here. So this is as an example, let's take some typical example of X. So it could be a cotangent bundle to Grassmannian of K hyperplanes in Cn, right? Then the quiver variety looks like this. It's an A1 quiver, so there's a single node. There's a framing here, right? And then, well, there are two maps this way and that way. So then so here we have so the classical K theory of X is described by tautological vector bundles, tautological vector bundle V of rank K, and then the trivial bundle W of rank N, right? And then as well as, so you can take these bundles, you can take their tensor products and you can multiply by the duals. Right. Good. So, yeah. And then in this case, there's a single scalar parameter z, and if the rank of this bundle is n, then there are n equivariant parameters a, and then there's also parameter h bar. So equivariant torus in this case is n plus one dimensional. Scalar torus is one dimensional, and then so you have this classical K theory. Classical equivariant K theory of X, right? So it's an algebra, right? It's a cumulative algebra. The multiplication is the tensor product, right? And elements of this algebra are those bundles and their tensor duals. So you can compute something like V tensor V dual, tensor, I don't know, lambda to the K V and so on. Now, so that notation with so that means the following. So Z q to the L. So this is the multiplicative notation for the shifts. So if your Kähler torus, if your Kähler torus is a tuple of L variables, right? So same L is here, like the number of nodes in the quiver, then, well, so that notation means that you simply shift. So like if you take your line bundle, your bundle L, and you expand it in the basis in the Picard group, then this is what you're going to get. Where the, well, if L has the following decomposition, so if there's L1, right, so these are line bundles. So L1 to the C1 tensor and so on tensor, LL to the CL, and these are line. It's just the expansion of the, it's like essentially tells you that, well, in this vector space, you're making a shift in a certain direction. And so, yeah, in this example, Kähler torus is one-dimensional, so there's only kind of one shift, and then in general, you can have this kind of thing.
So what is the relationship between X and V cross this structure, lambda expression?
It's just an example of an element in this algebra, right? Yeah. This is L. This is L. Ah, thank you. Yes, thank you. Yeah. Other questions? Yeah. Okay. Now, okay, what else? And then the so psi of Z, A, and Q is the fundamental solution. Right, of the equation, and then and in terms of the difference equations, so it's a certain fundamental solution. But in terms of numerative geometry, psi is what is called the capping. Well, you can put quotes if you want. Capping operator, and that means the following. So this is how the construction goes. So you can, for any quiver, right, you can define this algebra, right? And then you can study its quantum deformation. So, and this is done by means of enumerative geometry by counting this quasi-maps into, also by counting maps of this CP1 into X, right? And then, well, every class, let's call this class tau, right? So every class in equivariant K theory, you can lift to the class in the moduli space, right? And you can evaluate this, right? So, and every such class will have an expansion, so it will be, say, tau with a hat, it will be a full quantum version, which in expansion starts with a classical expression, and then there will be certain series in quantum parameters in Kähler. Yeah, that's right. Well, so it depends on the quiver, right? So in this, like, it depends on the dimension of this tori. Like, so for example, in this example, it will be what, like n-dimensional. Right. So yeah, and then in particular, you can take just identity elements. So there's like one trivial, you can take one, but then there's a quantum one, which is also, you know, there's some, let's call it alpha d z to the d. And then the tensor product also gets modified. It gets modified to what is called quantum multiplication, right? And then the questions you can ask is that, well, how, if I have my quantum classes computed through this moduli space, how they talk to each other, right? So basically, if I have two classes, tau and say, you know, mu, like, how can I describe this multiplication? And it turns out that, well, you can make it work, and then the quantum K theory of quiver variety X will be also in algebra. It will be commutative and unital, and then this one will be unit with respect to multiplication star, which is the new quantum multiplication. Now, I haven't finished talking about psi. So now, so this is a highly singular space, right? So it has, if you try to work with this directly, you will encounter some problems, right? So instead, you have to introduce some computifications, and then there are a couple of ways to do it. So first, you can introduce so-called non-singular boundary conditions at 0 or infinity. Right, so all the evaluations, all those classes are evaluated at fixed points of the torus, so it's either 0 or infinity. So therefore, you would take your class, and then when you lift it to the moduli space, you need to do the evaluation either here or here. And when you do it, you need to make sure that it works, that it makes sense. So you can just say that the singularity of your quasimap does not go to 0 or to infinity. So those quasimaps are called non-singular. So that's one way to do it. Now, this modular space is not proper, which causes some problems. But however, because of the for those quiver varieties, at least in the subclass that we're studying, all the fixed points are isolated. Then you can actually do the integral. And then second example is what was called relative quasimaps. So let's say for concreteness, let's say we put non-singular conditions at 0. We're going to put relative conditions at infinity. And that means the following. It means that if the singularity approaches infinity, then, well, you can actually blow it up. So you can blow it up by P1, and then if it's still singular, you can blow it up again and again and again and again. And we know that this process will stop at some point because f is a polynomial of some finite degree. So psi, roughly speaking, is a partition function. It's like a quantum K-theory class of 1, provided these boundary conditions. So more or less psi, so this capping, right, it's the partition function, was written in this loosely physics notation. So of the moduli space of quasimaps into X, right, with non-singular conditions at 0 and non-singular boundary conditions and relative at infinity. And then you can define this object, you can calculate this, and then you can show that, well, it actually satisfies this Q difference equation. Well, they depend on these parameters here, right? And then if you swap them around, you're going to get the different functions. So then they'll satisfy the same difference equation here. Like, so like maybe more physics, like say conformal field theory, study word identity, right? It's some kind of difference or differential equation. You can have several solutions. And those solutions will be related by, in this case, Weil group action, permutation of these elements here. Yeah, that's right. So in fact, so like, since you asked, in fact, so psi are usually labeled by 2 indices. There's like one index labels the solution of the equation, and then another one labels the component in this vector, right? So it's a whole matrix full of solutions. Yeah. Other questions? Yeah, like, let me give an example. So what does this mean? So let's say X is, again, let's say X is just P1. It's not a quiver variety, but it will do for the example. So Riemann sphere, you can write it as the, in the uniform coordinates, right? It's the ratio of projective coordinates U and V, right? And then each of those U and V is a polynomial of degree D. Okay? So if roots of those polynomials are different, you're going to have degree D here, degree D here, and degree D there. However, if those roots become coincident, you can cancel some of the factors, and that messes up the degree quasimap count in degree below. So, and then what you want to avoid is that this root, excuse me, that the singularity does not approach 0 or infinity for that matter. And relative, you can blow it up, so like it will go here. Okay, so yeah, good. Now, right, and then so essentially a lot of information in enumerative geometry can be extracted from this equation. There's a similar difference equation when you shift the equivariant parameters. So there's a similar operator to M when instead of shifting the Cayley torus, you shift the equivariant torus. Yeah, and then kind of these two equations, they kind of they come in simultaneously. Okay, good. So this is the kind of geometric setup that we're working with. Now, it's what is called a flat Q connection, meaning that if we have, so, well, I'm going to write a fancy version of what is called Bianchi identity, right? So in differential case, you have two covariant derivatives commuting, right? And then you have, integrability this way. In this case, I have Q difference equation. So if I do this shift operator in L1 and L2, right? So in this direction, then, well, I can write it as first like this, ML2 ZQ to the L1. I'm going to suppress the other variables, ML1 of Z, right? I can shift first along L1 and then shift along L2. Or I can do it the other way around, right? I can do it like, okay? And then, well, so if I define curly M, so first I shift around L1, and now I'm already in this kind of shifted Q grading, and then I shift in L2. Yeah, this is L2, and this is, or yeah, thank you. Hold on, 2, thank you. Yeah, good. And then, so what I'm going to do, well, maybe as you can see from title, so essentially the game I'm going to play is the following. So given this Q difference equation, I'm going to take different stationary limits. So first I can take the limit as Q goes to 1, and that's the standard one, right? But then I'm going to do something more fancy. I'm going to introduce the slightly different operator. I'm going to send Q to the primitive root of unity, to the pth root of unity. And this is where all this p-Curvature stuff will appear. Okay, so now I wrote it like instantly like this. We have to actually need to prove that this works. And it's highly non-trivial statement that, if you introduce your object M, the way kind of I sketched here, the limit even exists, but it's true, right? And then, well, so, and then if you look here, so as Q goes to 1, this equation becomes the commutativity relation for my operators M, right? So from here, it follows that the curly M's, they commute, right? And then that's what people call, this is the geometric origin of integrability. Right, so in integrable systems, you have like usually, okay, no, integrability is like art and science of mathematical physics, right? And like, it's always hard to prove that system is integrable, but like, if you have this magic matrix M or whatever, so which depends on some parameters, in this case, M depends, once Q is gone, it depends on Z and on A. So if you take a characteristic polynomial of M and compute its coefficients, say in Z, you'll get some, so those coefficients will be integrals of motion of some integrable model. In this case, this is XXZ spin chain. So it's a one-dimensional lattice model, which has a Hamiltonian, just some kind of matrix, right? And then you can show that it has as many conserved charges as the number of sides of the chain, essentially. So in this case, if you take this Grassmannian here, it will be an XXZ spin chain on N lattice sites in the sector when you have K excitations. So you can kind of think of it as so it will be SL chain for SL2. So in the representation theory literature, people study this algebra here, quantum affine SL2, right? papers by Reshetikhin and collaborators, right, and some people in the room here. So, and then right. So the reason why it's SSL2 is because it's an A1 quiver. So the rank of the quiver gives you the Lie algebra in the spin chain, and then the geometric data of the quiver, so like the dimension of the equivariant torus and dimension of the Kähler torus will give you more details about what kind of spin chain that is. Yeah. Okay, so that's the first guy. That's the, well, that's the usual game. But now let's do something else though. So let's just say, let's do the, well, and yeah, and then it's solved by Bethe ansatz. I'm not going to write Bethe ansatz equations. Well, the talk is not about this, but essentially, see, if you send Q to 1, that equation becomes the eigenvalue equation for operator M, right? And then eigenvalues of M will be certain functions, right? And they will depend on, on all of those variables. And then in order to find, well, so there's a trick, which is, there's a way to find those eigenvalues by solving some set of auxiliary polynomial equations, which are called Bethe equations for the spin chain. Good. Okay, now let's talk about this more interesting element. Let's modify the story a little bit. So let's say I take ML. Again, pick a line bundle from Picard. I do ML. Then I do, so I shift it again. And I compose. And then I do it p times, right? So get more space. So let's call this guy straight M L to the P. Right, it's an iterated product of P operators. And at this point, P doesn't have to be prime. We're not doing number theory yet. So what I'm about to tell at the level of difference equations will hold when P is like 4 or 6 or whatever. It's only when we go down to differential connections, P has to be prime, and we'll get there. Yeah.
Can you explain a little more on type? Type is function or what type?
Yeah, it's some kind of function that you can, which is it's some kind of series, in Kähler parameters. You can explicitly compute it. Well, it's so it's a certain class in this K-theory construction. So there's some integral that computes it, right? So there's a covariant integration that you can do. You can write it either as an integral of some sort, or you can write it as an infinite Taylor series in Kähler parameters. I'll give an example for some simple variety later, but yes, essentially it's some kind of known function which we know how to compute.
These are two with the geometric series, right?
Good. So thank you. So yeah, so if you take, let's do an example. So if you take T star of CP1, so K equals 1, N equals 2, then, well, it's not the psi, but that guy, 1 with the hat, will be 2, phi, 1 of some. Yes, it will be the Q hypergeometric series of Kähler parameter, and it will be some ABC, which I don't remember. Anyway, coming back to Renat's question. So one of those coefficients will look like A1 divided by A2. And if you flip them, you get a second solution. So this thing satisfies a second order quantum difference equation, which is the Q hypergeometric equation. And then if you look at the formal series solutions, right, without worrying what happens at infinity, you'll have this one and the second one. Other questions? Yeah, and then, yes. So to get higher, look at the kind of my favorite example, if you take flag variety. So if you have T star G mod B, it will have n-dimensional Kähler torus and n-dimensional covariant torus. And yeah, that will be this one of those very symmetric functions that appear in this integrable systems literature. Yeah. In that case, oh, by the way, so okay, for those also who are fans of integrability, so that one hat, just a side comment, is an eigenfunction of well, if it's a flag variety in Cn, then it's n-body trigonometric or Rosinar's model. So, is there a Dutch person in the room who can pronounce it properly? Rosinar's, right? Anyway, so Rosinar's Schneider. It's a relativistic Calogero system. So it's like when you have particle, they move at relativistic speeds, and there's a many-body system which is integrable. So in fact, that construction gives you two integrable systems at once: the spin chain, quantum lattice model, and this many-body system here. And then there's a duality between them, which we call quantum classical duality. Upon which the, say, Kähler parameters here, so in this case, in this model, those Kähler parameters, they play a role of some twisted boundary conditions, and then here they will be coordinates of that integrable model. So like the Kähler torus of the flag will be literally the part of the configuration space of your TRS model. Yeah. And then upon this duality, the Bethe-Ansatz equations of the spin chain are equivalent to the energy level set of the equations in this model. Okay, let's get back here. So we do this iteration, and now I want to take I'm going to define the limit. So curly M, well, you may guess, and now say, if say zeta to the p is the pth root of unity, right? It can be primitive, but just take e to the 2 pi I divided by p, you'll be okay. So this thing defines is well, t to the p goes to 1. Again, highly non-trivial that it's even possible, but you can take my word for it. I mean, that this limit exists, actually. Again, and similarly, there's integrability. Integrability, so those guys commute. So if you take shift along L1, and then shift along L2, it doesn't matter in which order you do it. And then that provides some equivalent description of this integrable system. Good. Right. Okay, let me write the first theorem. Or maybe I can fit it here. So let lambda I be the set of eigenvalues yes, of M, L, Z, A, curly, right? So again, so take that equation, send this stationary limit, right? And then you'll get an eigenvalue equation for that operator. And then let's just denote the set of eigenvalues to lambda i's. Okay, then, okay, does anybody want to make a guess, if you do not answer, what will be the set of eigenvalues of this guy? So I want to say this is some explicit functions of A and Z. What will be the set of eigenvalues of the iterated one? Exactly. So this is what's called Frobenius, right? So you would do this. Then that is a set of eigenvalues And then, yeah, so there's this Frobenius operation that takes z and does z to the p. So it's like literally you don't do anything. It's literally the same function, and you just exponentiate all the variables. Okay. Good. Now next, theorem 1. Now let's so that's after we've taken the stationary limit. So now let's talk about get Q back, right, and then talk about this picture with the moduli space a little bit more. So let's introduce. Actually, never mind. Yeah, we're going to still do the M. So now define this operator. So we take psi, the capping. Okay, and then I take psi inverse. So again, so we should think of it as a matrix. I'm doing the Frobenius here, z to the p, a to the p, and then here comes the surprising fact, q to the p squared. I do the inverse, I take the limit q to the p goes to 1, and claim that this is finite. So the limit is well defined. So you actually have to, not q to the p, but q to the p squared. And let's call this f. Is well defined. And it does something interesting. So in fact, it provides the, so essentially, well, it's after this is done, the theorem 1 becomes a corollary of theorem 2. Well, so that's what happens. So ML, if you take the you can conjugate it with f. I think it's also labeled by the root, right? So z to p. I'm sorry. Let me do the. Yeah. Well, it's labeled by the root, but then the final answer does not depend on which primitive root of unity you are taking. So q goes to z to p. So now, if we conjugate this with f, so it's a matrix which is well defined. This is just a linear algebra. You're gonna get in other words, these two operators are isospectral. ML of z to the p, right, and of z. So there's an explicit similarity transformation. Now, what does it mean from the point of view of an enumerative algebraic geometry? So I'm going to come back to the picture a little bit. Whoa. And then, well, imagine that this is the following thing. So you have, well, let's just do this AG notation, right? So say this is the P1, the rational component, and then say here I have, well, so I told you that that psi, right? Psi is the partition function when you have non-singular conditions on one side and then relative conditions on the other side. Well, and then there's a psi inverse, but it's a bit different. So in a sense, like so what this function does is essentially it provides you a transition between the moduli space where on one side your quasimap count is manifestly z mod p invariant, right? So essentially that's what it means. Like if all your variables depends on their pth power, there's a manifest action of the pth root of unity group, right? And then kind of essentially that operator f, what kind of tells you, so here you have kind of normal, so you have kind of normal relative conditions. So this is normal relative. And here you have, well, z mod p relative. And you can construct such object. So this is what in number theory is called Frobenius intertwiner. Well, this is not exactly the Frobenius intertwiner yet, but that it will become one once we take the limit, which I'm going to talk about now. Okay, need to speed up. Okay, maybe I should do the example. Okay, maybe one more comment. So why p squared? Why q to the p squared? So imagine you are studying quantum torus relations. Say x and y are just some variables in A2 or C2, and you want to study the non-commutative deformation of C2, right? So you have x and y, right? So then if q is the non-commutativity parameter, then we'll have something like this, right? And now imagine I'm doing Frobenius on both sides. So if this is true, then, well, you can ask yourselves how x to the p and y to the p will q commute. What should I put here? So you need to pass y through, right? There are p of them. Each y gives me a factor of q to the p squared. So it will be q to the p squared. And then like on a more technical level, so when you do this calculation, this is some kind of placistic exponential. And then, well, so essentially you need to show that upstairs in the exponent, all poles cancel. And that this can be done explicitly. So. Maybe let me give the example. So where can I give the example? Or maybe there. I can erase this. $18 minutes. For example, if quiver variety is T star P0. Okay, so in this case, well, that difference equation looks very simple. So there's one-dimensional Cayley torus, and then the equation looks like that there are no A's, there's only H bar that dilates the fiber, and the solution looks like this. Explicit series. I'm not sure many if you can recognize the thing, and then, well, like you take this formula, and then, well, it's easy to check that this satisfies the difference equation. Like this kind of rational function pops up, right? And then, well, that thing on the right board on the bottom, the psi inverse, it is provided that you have q to the p squared, we will have the cancellation, and then you'll have a finite expansion. Okay, great. So now, so we need to get back to the main story. So what's going to happen? Yeah, so now since we know that these two Q connection matrices are isospectral, we're going to take a limit of both operators to the differential equations instead of difference equations, and then the guy on the top, this iterated product, will become the p-Curvature, and then this guy here will become some other connection which is easy to compute. Okay. Yeah, that's right. That's also that operator M is just a function. It's just a scalar function. That fraction there. Yeah, that's right. Yeah, that's right. So it's like Katz over the point. It still has non-trivial dynamics. Like there's when you study when you map, quasimap will go into the fiber, right, and then it will give you non-trivial contributions. So like classical K-theory retracts down to the zero section, but quantum does not, right? It still has non-trivial thing going on in the cotangent direction. Okay, now let's, so next section is p-curvature. So if I have time, I'll comment on the meaning of p-curvature later, but so for now, so first let's do the, we're gonna take the following limit. So if you take psi of q to the L divided by psi of z and then send q to 1, so this q logarithmic derivative becomes logarithmic derivative. So that becomes nabla I psi of z, where nabla I is zi d over zi I. Like I'm acting on the ith component, right? Oh, no, never mind. Okay, so like this, it's going to be a sum minus, let's call it S ci of ZAA, where this is the this is some Chorn classes. This is some kind of Chorn class. Whichever, or like, so essentially for every line bundle in K theory, there's some kind of Chorn class in cohomology. So if you want, this is the cohomology, the quantum cohomology limit. And S is a certain parameter that depends on, so it depends on H bar and Q. It's some kind of function of H bar and Q in this kind of cohomological limit. They all combine together. So think of it as just some parameter that comes naturally from geometry. Okay, now how exactly are we going to do this? Well, so if you say that Q is, close to 1, right, you can just do the first order expansion on epsilon, and you'll get yourself this kind of contribution. And similarly, kind of the Q difference operator, so what does this mean? If you have Q to the Zi d over dzi, this difference operator, well, again, so you're going to be 1 plus epsilon S, well, epsilon, Zi d over dzi, and so on. So this is the standard story. So that's how you would normally do it. But now, let's do it slightly differently. So in a sense, so that calculation, which many of us did in calculus class, or teach students to do in calculus class, is what happens when Q approaches 1 in C norm, like in norm, like regular norm in Rn or Cn. But now let's see what happens if it approaches 1 in p-adic norm. Now, 30 seconds crash course on p-adic numbers. So I'm going to, instead of ZP, I'm going to put QP. And so what's a p-adic number? So it's the following thing. So elements here are formal series. So now let's P be prime. Anyone? 2, my favorite prime is 2. Yeah, so we can ask, so yeah, P squared and so on. Where P is prime, and then, so here are those coefficients AI, they live in Z mod P. Right? And then there's a p-adic norm of valuation. Is that so the p-adic norm of P is 1 over P. So for the purpose of the series, it behaves like an epsilon, right? So series like this one will converge. Okay, so let's do a pop-up quiz. So what's your favorite prime number? 2 is already taken, minus 2. 5, good, 5, I like 5. Yeah, so what is it equal to? In Q sub 5. That's right, yeah. So it's a geometric series, right? So it's right. So that's what this means, right? So you can actually think it. So in Q sub 5, 5-adic norm, this series converges, like the sequence of partial sums of the series converges to -1/4. So that's what p-adic numbers are, right? It's like, it's, as a set, it's just rational numbers, but it has this weird metric, right? And it allows you to do interesting things. And one of them is I'm about to describe. Okay, now it's not, this ring is not yet good enough for us because our favorite number, the primitive root of unity zeta p, is not here. You can just check it, right? So like, there's no number which would be, it's simply not there, right? So you need to extend it. You need to find the ring extension. So we're going to introduce new element pi that satisfies the following conditions. So pi to the power p minus 1 is equal to negative p. And that will do the job. So if you do it this way, then still fine on time. Well, you can see from here that it's also small, so its periodic norm is what? Is 1 over p to the 1 over p minus 1. And because prime numbers begin from 2, right, 1 is not a prime number, so this is always less than 1, so it works. So it has a good periodic valuation. So I'm going to do some calculations. I'm going to do them mod p and mod pi. And if you have congruency mod pi, I'll have congruency mod p. Okay. So maybe mention one lemma, which kind of will show you the importance of this element here, pi. So if you take, so from now on, everything will be congruency mod. Oh yeah, one more thing, and then so if you take the integer subfield, subring, right? So z mod pz. So pi will be a maximal ideal in this ring over here, and if you quotient by the ideal, you're going to get the field. So z mod pz as a subring of qp, and if I join it with pi, mod pi is a field, and this is, well, let's call it fp, and it's a field. One of the first things we learn in commutative algebra is that if you have a maximal ideal, the factor of what maximal ideal is a field. So I'm going to work in this fp. So essentially, over fp, that operator reduced in this fancy way will become the Grothendieck Katz p-Curvature. Okay, 7 minutes. Good. So lemma. Now, if you take this pi guy and then do the calculation like this, then you're just going to open up the Newton binomial coefficients, right? And then you're going to calculate. So you'll see that you're going to get, 1 plus pi to the, what's going on? Give me 1 second. Yeah, pi to the p, alpha to the p minus alpha, plus order of pi to the p plus 1. So you see what happens is that the, well, again, you have 1 to the p plus this to the p, right? It's this and this. But then there will be another term when you get pi to the power p minus 1, okay? And then because of this condition, it will provide me another minus over here. And so this is true. And then because of this relation, it will bring some additional terms in formula like this. Okay. So, and now I'm going to do the reduce mod, reduce to fp to this finite field. So I'm going to expand q around 1, but in this new field here, ring, yeah. So over here, so plus order of pi squared. And then I'm going to do similar expansion of my q difference operator as I showed over here. So and now, instead of approaching 1 in C norm, I'm going to be approaching 1 in this new periodic norm. So that iterated product upstairs can be written like this. So if you take m li zeta to the p of z and aq, well, I can write it as an iterated product. Ml ZAQ, Q to the ZI d over dzi to the P, right? So you see, imagine you act on this with some vector, some section, and then you can shift it once, and then you can shift it again and again and again. And now I'm going to do the Taylor expansion of this guy with the pi. Okay, so now, and then using this lemma, I'll have contributions that are proportional to pi to the p. And then if you do the calculation carefully, the following thing will happen. So that MLI of ZAQ minus 1 over pi to the p is congruent to that logarithmic connection over there to the p minus nabla I. And this is Grothendieck Katz p-Curvature.
Can I ask you about?
Yeah.
This is the lemma. Can you apply the XXX spin chain?
What do you mean in particular? So like
No, you have the. Can you apply this kind of this lemma to spin chain XXX?
well, so M is the Lux matrix for XXZ.
Right. I
Yes.
understand.
Yeah, so like I mean, at this point, it's like it's like yeah. So I'm not giving anything new for the XXZ spin chain, right? It's like all the essentially these are the same eigenvalues as you have in your normal beta ansatz. With this trick, I'm getting different eigenvalues which are given by this formula. So it's same functions except that I'm doing the Frobenius on the variables. Yeah. Otherwise, everything we know about XXZ integrability stays. I'm not giving any new ingredients there. Yeah. So yeah. So like. After doing this expansion, we see that if you pick up the right terms, we get this pth power of the connection, logarithmic connection minus nabla, and then you can show additionally that well, also mod p is congruent to just differential connection times zi to the p, and when this is just normal differential connection, so like d over dzi plus stuff, right? And sometimes depending on the book that you're looking at, either this is defined as a p-curvature. Well, this is the p-curvature. So this is Grothendieck Katz curvature. It's an important object in analytic number theory. So, for example, you can, like in differential equations. So, if you study a space of solutions of an ODE over finite fields, right? You can have some full space of solutions, and then you can ask yourself, can you lift this full space of solutions to analytic solutions? Like, does the full basis exist? The conjecture by these two gentlemen, well, I mean, so Grothendieck has unpublished work, and then Katz has a big paper in the 70s, is that the answer is yes if p-curvature vanishes. So if the p-curvature of this connection in this formalism is trivial, it's like p flat, p-curvature flat, then for all but finite number of primes p, right? Then you can do the lift. Well, so let's do an example. So it's actually this kind of thing. You do the you differentiate as you would normally do, and then you take mod p. So let's compute squared. So let's do nabla. Say nabla is d plus a. I'm going to realize this as the differential operator, right? So d over d plus a. Then let's say I hit it on some section f. Yeah, so I like this exercise. So it's going to be dz plus a f prime. And now we're going to use another calculus exercise, Leibniz rule, right? So there's a second derivative, and then it will be a times f prime, and there will be another. Okay, let me write it down. So, and then here I do the Leibniz rule, right? So a prime f plus a d z a f prime. And now you see what happens is that I have two of them, and my prime is equal to 2. So it's gone. And then plus a squared. And now, well, you need to think a bit harder to show that this is gone, but essentially, if you think of your space of function as kind of Taylor series, in this case, you can only keep Taylor series up to linear term. So del squared also acts trivially. Okay, so this becomes a prime plus a squared. And you can always show that this thing is always a matrix. It's always derivative free. The combinatorics, however, is very complicated. So take a prime number over 1 million, do it. You can use the computer, but it's horrendous. So, and then one of the kind of questions was how to compute the spectrum of p-curvature, right? And our theorem provides the answer to that. So it's like, so from this guy, you get the p-curvature, and then from the other guy, you get, well, actually, let me finish because I'm out of time. So, good. So, yeah, so that's the p-curvature, right? It's an interesting combinatorial object in analytic number theory. And then my theorem tells you that it's, so if you take this iterated guy and reduce over this finite field, you get p-curvature. And if you take the right-hand side, right, if you take this guy, the Frobenius, you're going to get this. So ML, what are the Frobenius variables? Z to the P, A to the P, Q to the P minus 1. Again, I'm just collecting the terms in front of my favorite pi is equal to S to the P minus S. And then, well, so again, you would compute, it's just a normal connection, right? And then except that you work in this exponentiated variables, and it multiplies by this polynomial here, right? So remember, S was that parameter that I had in my reduction to cohomology, so it has some geometric meaning. And then because everything works mod p, so you'll notice that this polynomial is periodic. So if you shift S to S plus 1, it's periodic mod p. And so one of the magic formula from elementary number theory is that in the Pascal triangle, all rows are trivial. All prime rows are trivial, and that does a lot of wonders for you. Okay, so to wrap up, so yeah, so and then because of theorem 2, well, this connection, the p-curvature, is isospectral to this connection, and this is just a normal connection, and everything works. Yeah, so maybe I can write it down, and then I'm done. So. So yeah, so one's called Grothendieck Katz p-curvature. Oh, let's write it as a Frobenius map. So like it's a connection precomposed with Frobenius, right? So okay, that's it. Thank you.